Hello, thank you for tuning in to this presentation on modal analysis and resonant frequency monitoring of a freestanding rock tower. My name is Alex Dzubay. I'm a junior studying geophysics at the University of Utah, and my research mentor is Dr. Jeffrey Moore. To start off, I'd like to discuss an idea which is really central to this field of modal analysis, which is the concept of ambient vibration analysis. So basically, all structures are constantly vibrating at what are called normal modes, and those modes are controlled by the object's geometry and material properties. So really central to this idea is the phenomenon of resonance, which is a really incredible phenomenon where objects will, when they are vibrated at what are called their natural frequencies, the amplitude of those vibrations will increase significantly without any additional force. So common examples of this are in musical instruments, or it's actually how microwaves work, is that the water molecules are vibrated at their natural frequency. And so we can take seismic measurements of these structures, these rock formations, and by looking at these vibrational properties, we can learn information about the structural conditions of those rock formations. And by monitoring these vibration properties, we have a means to assess changes in the structural conditions as well. So the site for this research is off of the Cane Springs Road, just southwest of Moab, Utah. It is a 13 meter by 6 meter by 36 meter column of sandstone. And if you can see in these pictures, it's basically a whole slab failed off of this cliff. And this is almost like the one remaining piece. And it's actually fully disconnected. If you can see here in the central picture, there's a crack going all the way down to the bottom of the column. For this research project, we had 3 separate seismometer deployments, as I was working on the UROP in the fall and the spring as well. The first deployment was largely exploratory, as we were trying to find which rock formation in this area would give us the cleanest and clearest resonant modes that would work well for our research. On this trip, we set up site reference arrays with 3 component nodal geophones, and those nodal geophones are the smaller ones you see on the left. And 3 component just means they measure vertical motion, north-south, and east-west. And furthermore, a site reference array is so that we can compare the vibrational measurements from the site and reference nodes. And from that, we can determine which resonant frequencies belong to the column versus the larger cliffside. So after this first trip, we found that this column provided the clearest resonant modes. So we came back for a second deployment, where we left the site reference array for 3 weeks to see how the resonant modes reacted to changes in temperature and other weather phenomena. Finally, we came back for a third deployment, where we really wanted to resolve the resonant modes and get a clearer picture of the higher modes as well. And so for this trip, we used a broadband seismometer, which is more expensive. They have less instrument noise, which means it's just easier to get a cleaner picture of what your resonant modes and frequencies are. Now, getting into the results of these field measurements, we can work through our process for data analysis, starting with the image in the bottom right-hand corner, which is a velocity plot showing the ground motion on the column as a function of time in all 3 components. And by the way, the data shown on this slide is from that third deployment with the broadband seismometer. From the velocity plots, we can create spectrograms, which I don't have a picture here because they're hard to explain, but in general, spectrograms plot power of vibration as a function of frequency and time. And from these, we can build what is called a power spectral density plot, which is shown in the bottom left. And these plot power versus frequency and show you at which frequencies is the vibrational power highest when you take out instrument noise and wind noise and all things like that. Now, as you can see in this plot, there are 3 really clear peaks on the left-hand side, as well as other peaks further on in the plot. And so these are our first 3 resonant modes, and these are the natural modes at which the column vibrates continuously. And if you look at the table in the top, we can actually do a polarization analysis as well to find what direction these modes are shaking in. And so first, you can see that the polarizations are near 1, meaning that the modes are really resolved and they vibrate in the same direction constantly. It's not very scattered. Furthermore, if you look at the azimuth angles, you'll see that the first two modes are separated by nearly 90 degrees. And we'll later find that this is because one is vibrating in the same direction, parallel to the cliffside, while the other is vibrating perpendicular to the cliffside. So in order to complete the modal analysis, which is the goal of this research project, we need something in addition to the field measurements, and that is numerical modal analysis. So to do this, I created a 3D model in the program Blender using field observations of the rock column. We then took this 3D model and put it in a computer program called COMSOL. And then after giving the program the material properties of the column, like its density, as well as applying boundary conditions, which you can see in blue in the image on the right, COMSOL is able to mathematically calculate what the theoretical resonant modes of the column should be. Then we can compare the results of this COMSOL modeling process to our measurements in the field and see how well we have been able to model our column, as well as how effectively we're able to measure resonant modes in the field. So if you look at this chart on the left, it shows both the resonant frequency values and their polarizations for all the way up to 6 modes. And if you look closely, you'll see that we have very effectively matched between our field measurements and COMSOL modeling for all 6 modes, which when we started this research project, we were looking to find only 3 modes. We would have been happy with only 3. So we were really proud of this result, as it really shows just how effective this technique of ambient vibration analysis can be in resolving the modes of a natural rock formation. Now, just to show a few of these modes a little more clearly, starting with the first mode, you can see that it has a resonant frequency of about 1.8 hertz. And if you look closely at the image on the right, you'll see that there are arrows pointing into what would be the cliffside. So this first mode vibrates perpendicularly to the cliffside. Taking a closer look at the second mode, we see that it has a resonant frequency of about 2.8 hertz. And it's really the opposite of the first mode in that it vibrates parallel to the cliffside as opposed to perpendicular. Then the third mode has a resonant frequency of about 5.1 hertz, and this is the torsional mode. So this is where the vibrating of this resonant frequency is a twisting of the rock column, as you can see in the image on the right. Now, it's a valid question to ask, what are we really getting out of this, aside from just determining the resonant modes of the rock column? Well, for one, we can fit this rock column to a simple cantilever model. And using that and looking at the resonant modes, we can find some interesting properties of the column and really look at what would influence the resonant modes of it. For one, as part of our comparing between the COMSOL modeling and the field results, we were able to determine the global Young's modulus of the rock column, which was about 1.4 gigapascals, which is a really valuable mechanical property to know. In addition, we can potentially monitor these resonant modes to assess changes in the structural conditions of the rock column. So in addition to these outputs, we can also measure the spectral amplification of ground motion on the column at certain frequencies. And so we did this using data from our earlier deployments when we had both a site and reference seismometer. And basically, a general overview is you can think of it as just dividing the power spectrums of both seismic measurements. And you do this in a certain direction so that you can make sure that you're seeing what the resonant mode is doing to the spectral amplification. So for example, in this plot on the right, we're looking for the first mode, and you can see that there's no second peak for that second mode. And that's because we were looking at vibration that is only perpendicular to the cliffside, so that we can see how that vibration is amplified on the column in that resonant mode. And so as you can see, we have a really sharp peak here and an amplitude ratio of nearly 70 times. So that means whatever vibration the reference seismometer on the cliffside was feeling in a direction that was perpendicular to the cliffside, on the column, the amplitude of that vibration was 70 times as extreme. So that's a really high value for spectral amplification. So additionally, we can start to develop methods for tracking these resonant frequencies and seeing how they respond to different external stimuli like temperature or wind or freeze-thaw cycles, and see if these lead to changes in structural conditions. Because these frequencies, they fluctuate when the temperature changes and things like that. So if you look at the bottom plot, this is us tracking the resonant frequency of the first mode over the 2-week deployment. And so as you can see, the frequency varies quite a bit. It's going up and down with like a daily cycle, really. And that's because the column is being heated when the sun comes up, and then it's cooling down at night, and that changes the resonant frequency. And so if you look at the plot on the right, we can also, there's a delay between temperature and its effect on the frequency. And so by shifting the rock temperature graphs, we can figure out what that time delay is. And we found that for the first mode, there's about a 2.25 hour delay between the rock temp increasing or changing and then the column's resonant modes feeling that change themselves. Furthermore, continuing this same idea of frequency tracking, we can try to attempt to measure the sensitivity of the resonant modes to temperature change. And if you look at the image in the bottom left, we do this by plotting the normalized frequency values against temperature. And by normalize, I mean that we take the values for the resonant frequencies and divide them by the average value for the resonant frequency. So that way we get a percentage value for how sensitive these modes are to changes in temperature. So then, applying a linear trend line, we can then look at the slope of that trend line, and basically that is how sensitive these resonant modes are to changes in temperature. So in this case, the first mode changes by about 0.22% for every degree Celsius of temperature change. So in addition to that, we can actually observe that these sensitivities to how much the resonant modes change with temperature also change over larger timescales. So in the plot on the right, I've plotted our results for the mode sensitivity in all 3 deployments, and those are the blue dots. And when we applied a linear trend line, it applied really well, but you can also see with these gray dots, these are all the different values for mode sensitivity from each day of that 2-week deployment. So as you can see, the mode sensitivity varies quite a bit. And there's really a lot more research to be done until we really understand why this sensitivity changes on larger timescales. If it's a seasonal thing, if it's still related to temperature or something larger having to do with the internal structure of the column, there's a lot more research to be done in that area. On this topic of areas for further research and also the limitations of this research, first and foremost has to be the continual establishment of these methods. This field of ambient vibration monitoring and modal analysis of rock formations is really new. The first paper to be published on it came out in 2010. So there's still a lot of work to be done to making this a more widespread and respected technique of monitoring these resonant modes and really establishing why that's important to monitor. Additionally, there's a lot of room for research in gaining a better understanding of how and why resonant modes respond to different external stimuli. So this is what we're talking about with how the frequencies change and also how they became more or less sensitive to temperature. There's a lot of different factors that can influence that, whether it's temperature or wind or freeze-thaw cycles or internal damage. So there's still a long way to go before we can understand why these frequencies are changing exactly. And furthermore, this continued research can lead to how these changes in resonant modes might signify damage to the internal structure of the column. And that's really the end goal of the research, is to be able to monitor the resonant modes of these rock columns or other rock formations and know, based on how the resonant modes are changing, if that rock formation is in danger of failing anytime soon. And so to do this, you really need to measure a rock formation as it moves towards failure. And that's really hard to do. So there's a lot of room for research in that area. And finally, we really need to develop more realistic monitoring applications, because seismometers are expensive, and it's really not a great end goal application if you're going to leave a seismometer that's a few $1,000s on top of a rock formation and just be okay with losing that when the rock formation fails. So we need to find methods of using cheaper seismometers that can still resolve these resonant modes, and also these cheaper seismometers also need to be able to continually send data, otherwise the monitoring aspect of this fails. And with that, my presentation has come to an end. So if you have any questions, please leave them in the comment section of this YouTube video. I would love to respond to them. And thank you so much for listening.